Welcome students. Today we will learn about the Oersted's experiment, how Oersted proved that the magnetism and electricity are related to each other, and he showed that experimentally. And second, we will learn about the magnetic field lines around a straight current carrying conductor. Before this, you have learned in the previous video class that the magnetic field is basically composed of magnetic field lines, and these magnetic field lines outside the magnet are moving from north to south, and inside the magnet they are moving from south to north. And to see what are the magnetic field lines or the magnetic field around a straight current carrying conductor, before we discuss, we will start with the Oersted's experiment, how Oersted discovered accidentally that the magnetism and electricity are related to each other. Do you know, students, Oersted, the full name of Oersted is Hans Christian Oersted. In 1820, this great physician has discovered the relationship between magnetism and electricity. Before this, there was no evidence about the relation between electricity and magnetism. But this was the first person who gave the evidences that these two fields are related to each other. According to Oersted, he was working on a circuit, and by chance a compass needle, which is itself a magnet, a tiny magnet, was there, and when a current is flowing through the circuit, that needle shows a deflection. And this deflection indicates that the current carrying conductor, there is something is happened in the conductor when current is flowing through that. If we switch off in the circuit, what will happen? The needle reaches are coming to the back its original position. Means that because of the current, the deflection of the needle will take place. He used, for example, as per the Oersted's experiment, he used a straight conductor. Let this is the conductor XY. XY is the conductor. And let the current is flowing through this conductor from Y to X, in the direction of Y to X. That means from bottom to top. And if we place perpendicularly a needle over it, that means compass needle like this. We place a compass needle over this. This indicates this is the north side of the needle and this is the south side of the needle. When the current is flowing through this straight conductor, this needle over it shows the deflection. And this deflection indicates that this current carrying conductor becomes a magnet, and the opposite poles of the magnet always attracts. For example, you know that the current is flowing through Y to X. The current through which it is flowing, the north side of that needle, magnetic needle, moves towards the Y, and the south side moves towards the X. This is how the deflection takes place in the needle. Later on, the direction, about the direction of the needle. So where a current is flowing through the conductor, that conductor becomes a magnet, and the two magnets, the opposite poles of the two magnets will attract. So the Y side through which the current is entered, that becomes the south, and the north of the needle will move towards the south, and the south of the needle move towards the X, that is the north of the conductor. So this indicates, as per the Oersted's experiment, it is clear that any current carrying conductor behaves as a magnet. So this was the concept which was given by Hans Christian Oersted in 1820. Later on, another scientist that was known as Andrew Mary Ampere, he gave a rule. That rule we call as Ampere's swimming swimming rule. This rule was given by Andrew Mary Ampere in order to find out the deflection, the direction of the deflection of the needle when a current is flowing through the conductor. According to Ampere's swimming rule, if a observer, please listen this carefully, if the observer is swimming along the direction of the conductor, keeping this in consideration that the direction of the current is in the direction of the swimming, then what will happen? The needle, the north of the needle will move towards the left hand of that swimmer. That indicates if, for example, if a swimmer moves in the direction of the conductor, if the direction of the conductor is, observer is swimming in the direction of the conductor, in the direction of the current in the conductor, then the needle, the north of the needle will move towards the left hand of that observer. This indicates that the needle will move towards the left side, and that indicates if the direction of the current will change in the conductor, then the direction of the movement of the north of the needle will also change. So the deflection of this needle purely depends upon two factors. Number one, it depends upon the direction of current in the conductor, and also it depends upon whether it is above or below, whether the needle is placed above or below the conductor. The second factor is that whether the condition is if this needle is below the this conductor or if this needle is above the conductor. That is another factor, that is whether the needle is placed above or below the needle, below the conductor. So this was about the Oersted's experiment and the Andrew Mary Ampere's swimming rule. So this experiment purely indicate that the magnetism and electricity are related. When a current flows through the conductor becomes a magnet, and there is a magnetic field around that conductor, and that magnetic field is represented by the magnetic lines of force. Let us see, we will take an example, we will take another topic, that how the magnetic field lines are placed around a straight current carrying conductor. Okay, now we will take another topic, that is magnetic field lines around a straight current carrying conductor. Now you know the magnetic field around any magnet is in terms of magnetic lines of force. In this topic we will concentrate on three important things. One, that is the magnetic field line pattern, the pattern of magnetic field lines. Number two, we will find out the direction of those field lines. And the third, we will find out the magnitude of magnetic field strength. So these three things we will discuss, we will learn in magnetic field lines around a straight current carrying conductor. This is an activity based topic. Let us take an activity. We take a cardboard, and that cardboard is placed horizontally like this. This is a cardboard, and make a hole on the cardboard at the center of this cardboard, and take any insulated metallic wire and pass through this metallic wire through the hole of this cardboard. Now you will see that this insulated metallic wire is passing through this metallic wire, and you will see that this insulated metallic wire is passing through this hole of this cardboard. Now you will see that this insulated metallic wire is passing through this hole of this cardboard. Now you will see that this insulated metallic wire is passing through this hole of this cardboard. Now you will see that this insulated metallic wire is passing through this hole of this cardboard. Now you will see that this insulated metallic wire is passing through this hole of this cardboard. Now you will see that this insulated metallic wire is passing through this hole of this cardboard. Now you will see that this insulated metallic wire is passing through this hole of this cardboard. Now you will see that this insulated metallic wire is passing through this hole of this cardboard. Now you will see that this insulated metallic wire is passing through this hole of this cardboard. Now you will see that this insulated metallic wire is passing through this hole of this cardboard. Now you will see that this insulated metallic wire is passing through this the metallic conductor, insulated metallic conductor is placed through the cardboard at the center of the cardboard. Now, join the ends of this cardboard with the terminals of the battery and rheostat. So, we will take an activity, we take a cardboard and make a hole exactly at the center of the cardboard and place a metallic wire, insulated metallic wire through this cardboard, and the free ends of this conductor is connected with the terminals of the battery, rheostat, and a key. And a key. Like this. This is the experimental requirement for this activity. You see that we have to take a cardboard which is horizontally placed. Then we take any insulated metallic wire like copper wire, but it should be insulated and that should be straight and insulated, and that straight conductor is placed through the whole of this cardboard exactly at the center of the cardboard. That means this conductor is perpendicular on the surface of this, what we call as cardboard, and now the free terminals, free ends of this conductor is connected with the rheostat. It will be connected with the battery, terminals of the battery, and the key of the circuit. So when we switch on, and we will sprinkle certain iron flings over this cardboard because the cardboard is placed horizontally like this. Okay? So when we place iron flings over it and then we switch on the key, the current flowing through the positive terminal like this and then moves downwards in the conductor. Let the conductor is XY, that the direction of current is through X to Y. And we gently tap the cardboard and we will find that these iron flings will be magnetized and they will arrange themselves according to the magnetic lines of force around the straight conductor. And it has been found that these magnetic lines of force arrange themselves in concentric circles around the conductor like this. Like this. So these magnetic lines of force around the straight current carrying conductor are in concentric circles. So we find the first important, that is the pattern around a straight current carrying conductor, pattern of magnetic lines of force. So when a current is flowing through a straight current carrying conductor, that conductor becomes a magnet, and that magnet magnetizes the iron flings, and those iron flings arrange themselves according to the magnetic field around it. And we will find, it has been observed that these magnetic lines of force are in concentric circles, and the center is the exact hole of the cardboard. So, as per this experiment, we have found that when a current flowing through the conductor, that conductor becomes a magnet, and around this magnet there is a magnetic field, magnetic lines of force. According to those magnetic lines of force, these iron flings will arrange themselves, and we find that these magnetic field around the straight conductor are in the concentric circles, and the center of every circle is the center of the whole, basically, of that cardboard. So we find that the first thing we have find that the pattern of magnetic lines of force in a straight conductor are in concentric circles. Now we know that in magnetic lines of force, these magnetic lines of force have direction. If we see the bar, these magnetic lines of force are arising from the north and enters into the south. But inside the bar magnet, they are moving from south to north. But here, in the straight conductor, these magnetic lines of force have certain direction. These circles have certain direction. Now the question arises whether these circles are anti-clockwise or they are clockwise. To find out the direction of these magnetic lines of force, we use Maxwell's right hand thumb rule. So we use Maxwell's right hand thumb rule in order to find out the direction of magnetic lines of force around a straight current carrying conductor. So according to Maxwell's right hand thumb rule. Now see, students, if we take our right hand, this is my right hand. Now place your straight conductor. Let's observe the straight conductor is in your right hand and thumb is placed in the direction of current of that conductor, and curl the fingers. Now these curled fingers give the direction of magnetic lines of force around it. It indicates that if thumb gives the direction of current and then the curled fingers around that conductor is the direction of magnetic lines of force. For example, if we change the direction of current in the conductor like this, if the thumb is below, that means thumb gives the direction of current, then the curled fingers also change its direction. Magnetic lines of force also change their direction. Means if we use this right hand thumb rule, according to Maxwell's right hand thumb rule, take your right hand, place the straight conductor in your right hand and curl the four fingers, place the thumb in the direction of the current in the conductor, place the thumb parallel to the direction of the current in the conductor. Then if thumb gives the direction of the current in the conductor, the curled fingers gives the direction of the magnetic lines of force. For example, if we use this here, you see in XY conductor the current is moving downwards, then the thumb is placed, then the thumb should be placed like this. I will place thumb in the direction of current, so thumb is in the direction of current, then these magnetic lines of force are what? They are in anti-clockwise. They are in clockwise. They are in clockwise direction. But if we reverse the direction of current, then the direction of magnetic lines of force also changes. So here, these magnetic lines of forces are anti-clockwise. They are anti-clockwise. So the direction of magnetic lines of force are downwards, and the magnetic lines of force around are clockwise direction, like this. These magnetic lines of force are clockwise. So their direction is like this. So it is clear that in Maxwell's right hand rule that if the direction in the conductor is down from bottom to top, then the magnetic lines of force around are anti-clockwise, and if it is from top to bottom, then the magnetic lines of force are in clockwise direction. So we find the second important factor in this topic, that is the direction of magnetic lines of force. So to find out the direction of magnetic lines of force, we use Maxwell's right hand thumb rule. And as per the Maxwell's right hand thumb rule, when you place any conductor carrying current in the right hand in such a way that the thumb is in the direction of the current, then the curl fingers gives the direction of magnetic lines of force. In a simple ways, we can say if the direction of current is from top to bottom, from bottom to top, then the magnetic lines of force around are in anti-clockwise, like this. They are in anti-clockwise direction. If the current is flowing from top to bottom, then the magnetic lines of force are in clockwise direction. They are in clockwise direction. Okay. So now the third important factor is magnitude of magnetic field strength. So magnetic field strength, these magnetic lines of force create magnetic field there. And there should be, what is the strength of this magnetic field? And what factors determine the strength of this magnetic field? So the magnetic field strength, the magnitude of magnetic field strength is given by B. It is represented by B. So we will find out. Students tell me this conductor becomes magnet because of current. Because of current. So it becomes conductor. It becomes magnet because of the current. When current is flowing through it. So when current is flowing through, that means current is the one of the important factor that makes this conductor as a magnet, which brings the magnetism or magnetic properties in the conductor. So we can say the first important factor on which the magnitude of magnetic strength depends, that is the magnitude of current. The first factor is magnitude of current. Magnitude of current. I. So magnitude of current, this magnetic field strength in straight current carrying conductor is directly proportional to the magnitude of current. As you increase the magnitude of current, the magnetic field strength will also increase. So we can say the magnetic field strength is directly proportional to the magnitude of current. So we can represent that B is directly proportional to I. As the magnetic field strength is increased, as the current in this conductor is increased, the magnetic field strength also increases. If we decrease the magnitude of current, the magnetic field strength also decreases. So they are directly proportional to each other. Let us consider this B is directly proportional to I as an equation first. Now second, see this conductor, the length of this conductor. This length of the conductor also determines the magnetic field strength. You know, for example, if we take one conductor, let's take this conductor, and this conductor, the maximum, the magnetic lines of force, if we see, is 1, 2, 3, 4, and 5. And in this conductor, it is smaller conductor than this. We find that here only 4 magnetic lines of force, 1, 2, 3, 4. So as the length of the conductor will increase, the magnetic field lines around it also increases. Because the magnetic field, the region will increase. So magnetic field lines also increases. So the length, as the number of magnetic lines of force increases, magnetic field strength also increases. So we can say the second factor is the length of the conductor. Length of the conductor. So length of the conductor L. So we can say B is directly proportional to L. As the length increases, the magnetic field strength also increases. Now, dear students, there is a third important factor. You know that when these magnetic lines of force arises, they are very close to each other. And the closeness of these magnetic lines of force gives the strength of magnetic field. As we move from the center towards the periphery, if we increase the radius of what? These circles, then the magnetic field strength will decrease. Why? Because these magnetic field strength, as they comes out, there is a larger distances between them. And as the distances are increased, what will happen? Then the magnetic field strength will decrease. So if we move from the center towards the periphery, or rather we can say if we increase the radius from the center towards the peripheries, then what will happen? The magnetic field strength will decrease. So we can say the radius of these circles, concentric circles, will decide the magnetic field strength. As the radius increases, field decreases. As the radius is smaller, the field is stronger. Means radius is inversely proportional to the magnetic field lines. So we can say the third important factor is that the radius of these circles, and they are inversely proportional. So B is inversely proportional to 1 divided by R. So combine these three equations. If we combine them, we will find out that the magnetic field strength B is directly proportional to what? I L divided by R. This is the total magnetic field strength around a straight current carrying conductor. So in a straight current carrying conductor, the magnetic field strength depends upon three factors. One, the magnitude of current. Second is the length of the conductor. And third is the radius of the magnetic lines of forces. Okay. So this is what we call as the magnetic field pattern, direction and magnitude of current, magnitude of magnetic field lines around a straight current carrying conductor. Dear students, you know that magnetic field strength, the unit of measuring magnitude of magnetic field strength is Tesla. Is Tesla. It is represented by capital T, Tesla. And this name was, is given from the great scientist named as Nikola Tesla. On his honor, in order to honor his name, we use the unit of measuring magnitude of magnetic field as Tesla. You know, this 1 Tesla, 1 Tesla is comparable. If we compare 1 Tesla, this 1 Tesla is equal to 0.3 into 10 raised power minus 4 Gauss. The Gauss is the smaller unit. The Tesla is the bigger unit. The smaller unit is the Gauss. And Gauss, 1 Tesla is equal to 0.3 into 10 raised power minus 4 Gauss. And if we see this 0.3 into 10 raised power 4 Gauss is basically the magnetic field strength of Earth's magnetic field on the surface of Earth, near the surface of Earth. Okay? So this is 1 Gauss. If we take 1 Gauss is equal to 10 raised power 4 Tesla. 10 raised power 4 Tesla. So you got an idea that the measuring unit for magnetic field strength is Tesla. This is a bigger unit. The smaller unit is Gauss, G-U-A-S-S, Gauss. And 1 Tesla is equal to 0.3 into 10 raised power minus 4 Gausses. And 1 Gauss is equal to 10 raised power 4 Teslas. This is the unit of magnetic field strength. To measure the magnitude of field strength, we use a unit as Tesla. And this Tesla is given on the name of great scientist Nikola Tesla. It is the honor to that great scientist. And this unit, Tesla, is a smaller unit, and we use the bigger unit, another bigger unit that is called Gauss. And Gauss is another unit to measure the magnitude of field strength. Thank you very much, students. We will continue this topic in the next video class.